Hi everybody, sorry about that, a little technical feedback. I'd like to introduce you to Espen, who we've got joining us remotely. So over to Espen. Thank you, Espen.
My name is Espen Tellefsen. I'm the CEO of mLogic. It's a design center for embedded systems and FPGA based in Norway. So I'm also the author and architect of UVVM, which I'll talk about in this presentation. So I've always had a strong interest in pragmatic methodology improvement, and UVM is really a result of that. So before I start, I just want to say a few words about mLogic. So it's an independent design center for embedded systems and FPGA based in just outside Oslo in Norway. We were established only 3 years ago, but we're already 43 persons, and that includes 15 on FPGA, so we have an extreme ramp up. We do verification, IP, and methodology improvement through UVM and other stuff. We do also courses. I'll briefly mention that in another slide. So let's start with UVM. So what is UVM? It's a universal VHDL verification methodology. It's a library and methodology, can be used for FPGA, ASIC, and CPLD. It's free, it's open source, and it has a very structured infrastructure and architecture, but more important is that it allows the users to have or get a good infrastructure, good architecture in their own test benches. And that significantly improves verification efficiency and assures a far better design quality. UVM is recommended by Doulos for test bench architecture. We work closely with ESA to extend the functionality. I'll come back to that as well. And you'll find UVM on the IEEE Standards Association open source project and on GitHub. And it runs on any VHDL 2008 compliant simulator. So if we look at test benches in the industry, what we see at the architecture for test benches is normally far worse than for design. They're far worse structured, documented, and coded. And we tend to waste far more time on verification. And I would say there's on average maybe an improvement potential of 50%. Based on what I have seen in different companies and what I've heard from various designers. And also, I think the test bench quality could be significantly better, allowing also, of course, the product, the FPGA, to be far better. And going back to the test bench, that in itself could be much better for finding bugs and that way being far more efficient. So I normally show this figure here when I do design courses, and that's because these things are so important. We need to have overview and readability. That's the most important thing in any design. Modifiability, maintainability, extensibility, equally important. Debuggability is extremely important as well, because according to Wilson Research, we spend 25% of the total project time on debugging. And of course, everybody talks about reusability, so that's important. And when you look at design versus test benches, basically we should have the same approach to achieving these goals. Have a basic infrastructure, we should divide and conquer at all stages, and most important, we should prioritize the reader at all times. That means we have to focus on the architecture. Architecture is basically key to all the things I talked about, and simplicity where needed the most. And we do have the same challenges as well, and I think the main important challenge is awareness. Awareness of the importance of doing all these things. Awareness of how much time we actually waste on doing things the wrong way. And these are the things we try to target with the UVM system. So I want to look at different parts of UVM in this presentation. Of course, I cannot go into details on every part, but I'll try to cover most important parts here. So I start by looking at the utility library and BFMs. just a brief presentation on that, a slide or two. So in this case, a dead simple device in the test, an interrupt controller, has a clock and a reset. It has a simple bus interface, which is just a simple register interface to allow you to access the internal registers. Then we have n different interrupt sources, and we have the resulting interrupt to the CPU. Of course, for this device in the test, we want to make a test bench. And the first thing we always need to do is to make a clock generator. This clock generator is extremely easy to generate or to use from the UVVM utility library. You basically just take the procedure, the clock generator procedure, one out of many, by the way, this is a simple one. Take that from the library, instantiate it in the architecture. And this is all you do, clock generator, call the procedure. And when you call that procedure in the architecture, that doesn't work as a sequential procedure as you normally do it in a process, but it works as a real separate standalone process. So this procedure inside the architecture is a so-called concurrent procedure and allows you to do a very, very efficient reuse of processes. So now you have a clock generator, and of course you need your test sequencer that is going to handle your test sequence from start to finish. And I always tell people you have to make log messages because that's important both to see that something is happening, to see what's happening, to see the progress, and for debugging. So we have a simple log command for that. In this case, we use an additional parameter, ID log header, that is for booster control, but it also, in this case, determines the layout of that message in the log file or in the transcript, or not or, but both. Then, of course, you're going to check values over and over again. In this case, we're checking that the value interrupt to the CPU is 0. And then there's a message, a string, as a third parameter. This is mandatory in UVVM. We were discussing whether to make that optional, but we decided we want to have a good methodology. And a good methodology means you should actually state what you're doing. And it's much better to do that as a string inside a command rather than -- as a comment. In that case, you can see the result below. You have the timestamp, you have the actual command, and the message. Then we very often want to check that a signal has been stable. We cannot do that by checking the value all the time because that doesn't prove that it has been stable. And in this case, we're just checking that the signal interrupt to the CPU has been stable from reset time, which is in this case as a timestamp, up to now. And let's see the result of that. Then in this case, of course, we want to generate lots of pulses on the interrupt source inputs. So in this case, we generate a pulse on the interrupt source, set it to 1 for 1 clock period. And one important thing with all test bench or any test bench is that you should never wait for something without a timeout. So in this case, for instance, we're waiting for the interrupt to the CPU to go to 1 at the earliest after 0 nanoseconds, at the latest after 2 clock periods. And that allows us to make sure that if this interrupt to the CPU never actually is set to 1, we will not wait forever. There will be a timeout and we will get an error message, alert message. And I just want to show you also how you can also combine this with bus functional models. In this case, a really simple write procedure to write to this SBI, simple bus interface or processor interface, whatever you call it, to write a value to the trigger register inside that module. And again, you can see the transcript below. This, by the way, is a simplified transcript. I left out the prefix, the message ID, and the scope, different columns that will be included here, or they're optional. but just in order to make it easier for you to see it in the transcript here. All these procedures are with positive acknowledge, and that's extremely important when you want to debug your test bench in the first place. But of course, these positive acknowledges must be possible to remove when you're running a more sort of complex test bench, large test bench. And you do that by verbosity control. Of course, alert message, mismatch reports, and so on are also important. I'll come back to that. And of course, counting the alerts and controlling how to handle them. Then these are some more commands, features, procedures that are available from inside this UVVM utility library, the lowest level of UVVM. And I think the most important things to mention here are the different types of clock generators, check for stability, generate pulse, and the semaphores with blocking flags, await barrier, and so on, and the verbosity control, enable log, disable log, and so on, and so on. You can have a look in the documentation and you can see all the different commands that are available. We have had basic randomization in UVVM for very many years, and I'm not going to go through that. I'm just going to show you one simple example in bold here. So that's how you would generate an integer, a random integer between 4 and 245. So you can see that's dead simple. And I think this is still the simplest possible solution for simple randomization. But then a couple of years ago, we introduced what we call enhanced randomization or advanced randomization. And the most important thing here was, of course, to have this tightly integrated with UVVM, with alert handling and logging in particular. Again, we have a strong focus on overview and readability. That's extremely important wherever you go in this system. And in order to improve the overview and readability here, we have added keywords to ease the understanding. So let's take one example. I don't have time to look at different types of randomization, but let's just show you the sort of basic standard approach here, where we do randomization in one single command. And generating a simple random number is always easy. In this case, everybody easily understands that in this case, you generate a number between 0 and 18. The syntax is easily understandable and couldn't really be different. But more complex randomization is normally more difficult to understand because you have more numbers as your parameters for different things. And having multiple numbers in a command, then it's always difficult to understand what these different numbers actually mean. But there are ways to significantly improve that. And we do that by adding enumerated in this case. So in this case, you can easily understand that we generate a random number between 0 and 18, but excluding the number 7. Or in this case, adding the numbers 30 and 31. Or we can do both, add some numbers and exclude some numbers. And imagine if you didn't have these enumerated, how difficult it would be to actually understand what the different numbers actually mean. We have the similar readability focus for weighting. So for instance, for a weighted randomization like this one, we put the order of the parameters in the procedure call. So in this case, you can see that the value comes first and the weight comes afterwards. So the value of 0 is given a weight of 2, value 1 is given a weight of 3, and so on. Same applies with a range and a weight. Then first comes the range and then the weight. That means in this case, we generate a random number between 0 and 18 with a weight of 4, and between 19 and 31 with a weight of 1. So you can easily understand the actual randomization and what you will get. So, but then some people says, well, this means there's more characters to write. You have to write this add and exclude. And yes, that is definitely correct, but typing code like this consumes a totally insignificant part of development time. Reading and understanding code on the other side is repeated over and over again, and that is important. So investing in better code yields, in my opinion, a huge return on investment. These extra characters improve readability a lot. And it makes it easier to, of course, maintain and extend as well. Let's jump to the next subject, functional coverage. So what is that? Well, it's a user-defined metric that measures how much of the design specification has been exercised in your test bench. So for instance, has various functional scenarios been tested? One example could be a UART. You could check whether the payload has started and ended with both 0 and 1. You could check has odd and even parity both been tested, and with the payload variations above. That's a cross coverage. And has selected cases of baud rate versus clock rate also been tested, and so on and so on. This requires a manual process to set up all the different wanted scenarios. That could be time consuming, but this is a great approach to check that various specific scenarios have actually been verified. So I won't go through the sequence of actually entering this functional coverage, but I just want to show you the reports that you can get when doing this. We have other webinars where you can find the syntax or how you actually set up the coverage. But as I said, I don't have time to show everything here. So in this case, we see the report for one single cover point. It's called cover point 1. That's the default name, unless you've given it a different name. Then you can see all the different bins that you have defined. Then you can see the bin coverage and the hits coverage. Bin coverage being 60% because you can see that 3 out of 5 bins have reached 100% coverage. And the hit coverage is slightly higher because you also have some coverage in other bins. And having those two parameters, I think, is a good thing. But of course, what you want to do at the end is report all the different cover points. And you don't want to actually have to sort of remember and know about all these cover points. So there's a dedicated command which allows you to report all cover points existing in your design, in your test bench study. So here you can see all the cover points and all the statistics for those cover points. I talked about randomization, and normal randomization is basically totally independent events. That means once you do one single randomization, that doesn't affect the next randomization. That's a normal way of handling randomization. Optimized randomization, on the other hand, is slightly different. That is randomization without replacement. So for instance, if you have a bucket of balls and you have 2 blue balls, then of course you have a probability of 40% of picking a blue ball. If you have normal randomization, you will always have 40% every single time you pick a new ball. But in this case, with optimized randomization, you pick out the blue ball, and then the next time around, there's only 25% chance that you will get a blue ball. So it's weighted according to target distribution and previous events. So let's assume, for instance, that we have a protocol payload of 0 to 256 bytes. Then we have some corner cases that we want to check. And corner cases in this case would be a payload of 0 or 1, 255 and 256. And of course, we also want to have something in between. And optimized randomization will yield the lowest number of randomizations for any given target. You set the target, and that's the number of occurrences you will get in random order for all these bins. That means a major reduction in number of packets and in simulation time. Jumping to the next subject, specification coverage, also known as requirements coverage, requirements tracking, and so on. This assures that all the specification requirements have been verified. So that means, of course, you have to have a list of requirements. has to be specified somewhere. And then you take that and make a comma-separated file and introduce that into your test bench. Then you report coverage from all the test sequences you have, whether that's one or many, or other test bench parts, and then you generate a summary report on coverage per requirement, test cases covering each requirement, and requirements covered by each test case. This is what's called the requirements traceability matrix. This is mandatory for safety and for mission-critical projects. So ESA, for instance, has a strict requirement on this. And I would say it's also strongly recommended for any project where you need good quality assurance. There are expensive tools existing, but this is actually a free and open source tool, which allows you to do what you need to do. And you can, of course, accumulate specification coverage over multiple test cases. And there are also free solutions, open source solutions that exist to report that a test case has finished successfully. But reporting that a test case has finished is not sufficient because that only allows you to do basically one requirement per test case. So what if multiple requirements are covered by the same test case? Because this is something you would like in order to reduce simulation time. Let's assume again this motor control that you're doing some kind of acceleration first, then you reach a top speed, you decelerate, and you reach the final position. You could, of course, have 4 different test cases for those 4 requirements. But this happens in sequence, so it is much more efficient to actually do it in the same test case and report those during the run. And again, to generate these various types of reports, as I just mentioned, and accumulate that over multiple test cases. That makes everything far, far more efficient. Now let's look at a dedicated test bench. Let's assume you have a BFM-based test bench for axis stream. In this case, a FIFO with an axis stream slave as input and axis stream master as output. Again, we have a clock generator. We can just instantiate that from UVVM. In this case, we don't have any test harness for simplicity. And as we use the BFMs, the sequencer will have direct access to all the signals of the device in the test. And that's great for simple test cases. But BFMs are sequential procedures that run in sequence in pmain. You could, of course, also run these procedures in separate processes. But the thing is that once you do that, you have to have communication between those processes to make sure that they know what the other processes are doing. Let's first look at the commands and the transcript here. So in the first case, we have an axis stream transmit. We include the byte array. We include the message, the clock, and the axis stream signals. It's a record for all the signals that go with this axis stream protocol. And then you can see the result of that in the log immediately below. So you can see that at timestamp 106 nanoseconds, the axis stream transmit was done. And as there's no alert, that means it was successful. Similarly, you can do on the other side with axis stream expect. You can expect an array and you check that and you get the same type of output. Then we can use this enable log message to add more verbosity. And when we do that, we can get a really good log where we can get detailed information about what's happening on this interface here. So for instance, when it's initiated, the various data words and that it has actually completed. Of course, for more sort of when we more into the test bench and everything is working, we're just checking larger packets and so on, then of course we reduce this information to far less. Also want to mention that these BFMs sometimes have more advanced features. So for instance, the axis stream, you can utilize more or less of the protocol, and you can define different word widths. I think that's default when you make a BFM. You should make it that flexible. But in this case, you can also configure the behavior. You can set maximum wait cycle, set to match data exact or just standard match, change endianness, and so on and so on. But what's even more important is that in this case, you can actually set the BFM to deassert T-valid or T-ready some cycles. And that can be done at fixed positions or randomly. And these features have enabled lots of bug detections in users' Axis Stream interfaces according to feedback. And this is just showing how, or some examples of how you can set up this configuration behavior to actually get the different types of behavior when it comes to deasserting T-valid, T-ready, randomly, or fixed. Now, what if we need to check this device in the test for simultaneous activity? I just mentioned that BFMs, of course, are running in sequence and consuming time. So again, back to this device in the test with the FIFO and Axis Stream slave and master. For a BFM test bench, we just looked at what that looks like. And as I said, these BFMs are great for simple test benches. They are dedicated procedures in a simple common package, and you just reference that and call the procedure from a process, test sequence process. Problem is that the process can only do one thing at any time. So you can either execute that BFM or another BFM or something else. You cannot do more things at any time. So to do more than one thing, we need to have multiple threads. And in the VHDL, that means processes, more processes or entities. So we could add processes on the interface here to handle the different aspects of these interfaces. Problem is that if we want to do that in a structured way and do things properly, have a proper check of this interface, there are going to be multiple processes here. And then we need inter-process communication, and that normally leads to chaos, as it would for design when you have multiple cores that needs to talk to each other. So for this, we need an entity component, and then we call that a verification component, and a defined protocol. So basically put all these processes into a verification component and make sure that they have a structure that is very well handled. Of course, the same thing on the Axis slave, on the Axis master side with a verification component slave. So what is verification components? This is an example with the simple bus interface as a verification component. And let's see what it looks like in real life. So it includes an interpreter, a command queue, and an executor. And as you can see, the verification component is now instantiated in between the test case sequencer and the bus interface, meaning that the test case sequencer is no longer accessing the bus interface directly. It does, however, interface and access the verification component directly. And when it does, the interpreter will look, is this command for me? If so, is that to be put onto the queue for execution? Or if not, then it'll just have a case structure on what to do. For instance, if there's a command to flush the queue, for instance. Then it comes through the command queue, and the executor will see that there's a command in the queue. It'll fetch that from the queue. It'll case on what to do. In the case of the SPI, it will check, is this a read, is this a write, is this a check command? And then it will execute that BFM towards the device under test. That means the verification component is also using the BFMs, but the verification component doesn't see that. It just sends the command to the verification component, and verification components handles everything else. So if now look at the Axis Stream verification component-based test bench, then we have the BFM-based test bench below. The verification component-based test bench on the top here. You can see verification components on both interfaces and on the clock generator. And then we have the main test sequencer again. And in this case, we need to add one more parameter or parameter set actually, which is a target. Because in this case, the test sequencer is not talking directly to the device and test, and there could be multiple verification components of the same type. So that means there has to be an additional parameter saying which verification component should actually this command go to, which verification component should handle this command. We could have a test harness if we want, and we can introduce that without changing anything in the hierarchy, because there are no signals going between the test sequencer and the verification components. They are all global signals handled by the system. So once you have this system, it's really easy to extend and modify. So this is the simple situation we had in the previous case. And I said we can case on what to do, whether that's a write, read, check, for instance. But we can also add local sequencers that could be more advanced. It could be, for instance, to be able to write, say 100 or 200 or whatever, or a number of different accesses on a given interface with, for instance, random data. That means you can send that single command from the test sequencer to the verification component. It's also easy to add checkers and monitors once you have this structure. We could add a bitrate checker, frame rate checker, and so on, and control those again from the test sequencer, enable them or disable them. And these checkers are far better included as parallel processes, as shown here, because that allows really simple inclusion and control, and it doesn't interfere with the test sequence. One thing that is very often very complex to handle with a normal test bench is to handle split transactions. So for instance, if you access the Avalon, then that will have a split transaction interface so that you can, for instance, do multiple read requests before you get the first read response back. And that creates chaos because that means we have to know which read requests we have actually executed and how to handle those afterwards. So it requires more communication. And in this case, it's handled very elegantly by the system. This was what we had as a start. We had an executor receiving the command from the command queue. It just receives a read command. And then executor knows that, okay, this executor, I will now execute, because there's a read command, I'll execute the read request BFM towards the device on the test. And then it will pass on the command it received to the next queue. And then there's a response executor that sees that, hey, there's something in the queue. Okay, it's a read request. That means there will be some data available from the device on the test soon. So I will issue a read response, and it will just stand there hanging until the device on the test responds with the given signal, and then it executes or continues to execute the response executor. This allows a very, very structured approach to handling this type of normally rather complex test bench issues. And it's also easy to handle out of order execution. The only difference then would be that the response executor receives a tag from the device on the test and fetches the relevant command from the queue. And of course, multi-thread interface handling is far better controlled as a pipeline in this case. And this architecture allows simple inclusion with queuing and control. And it allows the overview to be kept, and that's the most important thing for something that normally would create chaos. So we looked at these verification components, and what are the benefits of those components? Well, you can have simultaneous activity on multiple interfaces. That's extremely important. They are encapsulated, so you can have easy reuse at all levels. Queuing allows you to have multiple or initiate multiple high-level commands. You can have local sequencers, talk about that. And unique to UVM verification components is that you can control all verification components from a single sequencer. And then you can align them, and you can insert delay between the commands, so you can skew one interface with respect to another in order to reach corner cases, cyclomatic corner cases in your system. It allows simple handling of split transaction. Looked at that. We can have common commands to control VDC behavior, simple synchronization of interface actions from one single process. And that's important because that allows you to look at just one sequence of commands, have complete overview of what's happening inside your test bench. And of course, there are features to allow broadcast and multicast in this system as well. Everything allows you then to get a better overview, maintenance, extensibility, and reuse, as was our target in the first place. Due to the architecture of the verification components, the test bench architecture, and the command structure. Some people ask me, this is advanced. This is too advanced. And now I have the full picture up here. Advanced functionality, they say, is great when needed, but what if not? Well, if you use an existing verification component, well, just ignore it. Use it out of the box without the extras. That's simple. If you're making your own verification components based on this, well, just don't include the advanced stuff. Skip it in the VOC generator, or don't include it if you copy the architecture. And of course, if you don't want scoreboard transaction info, constrained random functional coverage, remove it. If you don't want these checkers, remove them. If you don't have the issue with split transactions, well, of course, you don't need this either. And then you're back to the really simple architecture. So we need simplicity where it's needed the most. We cannot have a complete test bench. The complete test bench cannot be simple everywhere if you have a complex device under test. So we have to make sure that we have simplicity where we need it the most. And as you can see here, we're back to the example with the Axis Stream 5 for verification components and so on. You can see the Axis Stream transmit and expect commands. And when you make a test bench and when you go through verification, basically you're doing three things. You potentially make verification components if you need new ones. You make your test bench with harness, but that's basically sort of Lego-like. You just connect them. And then you write n number of test cases via the test sequencer. But if you look at different scenarios and in different projects, okay, you might have project A here where, I have to make 2 or 3 new verification components. That's going to take some time. I have to make a complex test bench with these new verification components, but still, you spend almost a major majority of your time writing test cases, writing code in your test sequencers. So that means this is what we need to make the most efficient. Test sequence is by far the most time consuming, the most important to simplify, and especially for medium to complex device under test. So not investing in a good architecture means that the test sequencer time development will increase a lot. That's why it's important to be able to control things from the test sequencer with high-level commands like that. I mean, even software designers could write these commands and understand how it works. So with the UVM, there are lots of free bus functional models and verification components, which includes all the features I just talked about. It's the largest collection of VHDL interface models available. There's a list of all of them here. They are all free, they're all open source, well documented, and there are example test benches for every single one of them. We have provided our maintenance test benches not as a part of the UVM repo, but as a part of the UVM supplementary repo. You'll find it in the same place. And scoreboard is also an advanced feature that is important to have. So just show you one example of that as well. So in this case, again, we're back to the Axis Stream FIFO. In this case, we have verification components, and then now we also add the scoreboard. Again, we do an Axis Stream transmit to get data in. We, in this case, do an Axis Stream receive on the other side rather than an expect. That means we just want the slave verification component just to receive the data, not to check it. Then we can provide the data to from the Axis Stream master verification component, both through the device on the test and to an external device on the test model. That model will look at the transaction that was sent to the device on the test and pass on the expected result to the scoreboard. And then sometime later, the Axis Stream slave verification component will pass on that information to the scoreboard and check if that matches. So that means the model and the scoreboard allow functionality to be removed from the test sequencer, and that simplifies both the overview and the test sequencer. What we've done here is to make a standardized architecture that allows you to basically use any verification component made with this architecture in any system. That means you can share verification components with anyone, and they will work in your system for broadcast, multicast, for commands, for insert delays, and so on. That means it makes everything simple. The users know how the verification components behave and how the test harness will work. And as I said, verification components from different users will actually work together. Now let's look at the full picture. And again, look at the argument, is this too much? So we have the verification components connected there. I have a test harness. We might have our scoreboards as well. And we maybe have a model. We might even have a monitor here to check that what's actually happening if we, for instance, insert errors in the protocol. We could have a watchdog timer, an activity watchdog. We could even maybe have an Ethernet verification component here using hierarchical verification component, one going via the SPI verification component, the other in this case going via GMI. And the Ethernet component could also have its own Ethernet scoreboard. And that scoreboard would work on the Ethernet packets, not on the word level. And it could also, of course, have an error injector. So again, we have the question, is this too much? Do we have too many verification IP here? Is it too much structure? Okay, so these verification components are actually needed to check multiple interfaces if we're going to sort of allow the system to do skew on interface with respect to another. What if we simplify this? What if we remove all the stuff we just had there and just left with verification components? What happens then is that if you want to actually verify the functionality of your device in the test, that means you now have to start adding more procedures, more sequences and so on inside your test sequencer, add more support processes. And that means you're going to have you're going to have one test sequencer or multiple test sequencers with lots of support processes, and that's going to create chaos. Whereas if you have this structured approach, lots of verification components, but a structured approach, you know exactly what every single verification IP is doing. It's easy to understand what's going on. And debugging is much easier with a good architecture. So let's look at improving verification in general. Awareness, as I said, is extremely important. How to get the things that we want to have: overview, modifiability, debuggability, and reusability. This means we have to allow time up front to structure our test bench in the same way as we do for design. We should discuss our test bench architecture with someone else, with a sparring partner. We should have a walkthrough. And the same applies to control and status of all stimuli and checkers, how to reach corner cases and so on. And those could be both value and cycle related. There's a huge focus on value-related corner cases, but the cycle-related corner cases are equally important. Again, we need to divide and conquer at all stages. And the most important thing of all, prioritize the reader at all times. This is going back to the Wilson research on 22, where they say that half the verification time is spent on debugging. And I think we can be far more efficient than this. There's a huge improvement potential here. So if we assume a 6,000-hour project, then according to Wilson research, on average, we'll have 3,000 hours of verification. And how I see it is that these shaded areas is what we can actually remove, how we can improve this. And I believe with proper verification, with proper debug support, as you have with the UVVM, you could actually have a 50% improvement. And that on average. And that means, again, on average, that would save 1,500 hours. I mentioned I do courses. I will not go into detail on this. We do a pure FPGA and ASIC design course and an FPGA and ASIC VHDL verification course where all examples are using UVVM. You can just check our website for that. I mentioned I will just briefly talk about the new ESA UVM extension project. This was started up in March this year, and the first new functionality will be published now in June, hopefully in June. Otherwise, it will be in August because I have vacation in July in Norway, but I hope they will be published in June. And one or two things that are going to be presented is detection of unexpected or unwanted transactions on interface activity. Let's take a simple example again. A UART, we have commands that allow you to check that whatever coming out of the UART is correct with a UART receive command or UART expect command. But we haven't had any support for what happens if we don't expect anything on that interface and it suddenly starts doing something on that interface. That's not good either. This allows you to detect unexpected behavior. We also have completion detection that will also be added now. And that allows you to just with one single command, check or wait for every single verification component to finish, all the queues being finished, all the activity being finished, all the scoreboards being empty. So to conclude, UVM in a nutshell, I think there's a huge improvement potential for more structured FPGA verification in general. I talked about these things. They are extremely important. UVM targets all of this, and it's open source. It's free, available on IEEE and GitHub. It has the largest collection of interface models, BFMs, and verification components. We work together with ESA. That's available on GitHub and IEEE. It runs on every single VHDL 2008 compatible simulator. And this all has led to the usage really exploding. And as I said on the previous slide, UVM can actually save hundreds and in some cases even 1,000 or 2,000 hours, depending on the size of your project, of course, and depending on where you are today. And at the same time, it also allows you to improve time to market, mean time between failure, and life cycle cost. And I would also say that one thing that's important to think of here is that you can save the time by using a tool like this. And then you have saved that time, you get earlier to market, which is important. Or you can just save the cost. Or if quality is important and you have a deadline, then you will have more time available to do even better verification, which can also sometimes be very important. And that's it. Thank you.
Thank you very much, Espen.
Yep.
If anyone has any questions, would they like to type them in the Q&A or chat box?
Okay, so I see one question here. It's the question whether UVVM and OS-UVM play well together. I guess the answer is yes and no. You can easily use UVM together with any other approach, whether that's OS-UVM or your own legacy approach, meaning that you can, for instance, if you want the axis stream BFM or verification component I talked about, you can take just that BFM or verification component into your test bench and nothing else if you like. Or you can just pick specification coverage, for instance. So you can pick and choose whatever you like from UVVM and combine with anything else, really. The only limitation is that UVM has a verbosity control system and an alert handling system. And of course, in order to control that with UVVM, you have to use the UVM system. But if you have another system as well, that can work in parallel. But that means you can get both logs in the transcript, of course, but they will most probably go to two different log reports. Same with alert handling. You'll have to, for instance, set up both systems to stop after one error or something. So another question here: how's the reporting for integration into continuous integration tools? I think there's, well, first of all, you can use something called HDL regression. I should mention that. That's a tool that is also on GitHub that allows you to do regression testing in a simple way and compilation and everything. So check that out. But when it comes to integration into other CI tools, what you can, of course, take the result of every single test case and put that into these tools. But I think the best approach would be, for instance, to run specification coverage in UVVM. Specification coverage in UVVM will, for every single test case, generate a so-called partial coverage file, a CSV file. And if you only have one test case, you can use that CSV file directly and see everything. But if you have multiple test cases, then we have a Python script that allows you to take all the partial coverage files and generate a summary coverage file, which is also CSV, and you can, of course, put that into different types of tools. Those are the two only questions I see. Another one? Nope. Okay, so could I share the details on the number of people working on this project? If a bug in the UVM library is encountered, can it be reported, and how long will it take to solve it? Weeks, months, or years? Good question. So at the moment, we are two different companies working on UVVM. I think in both companies on the current ESA project, there are a total of 6 persons working on this in parallel. And then there's an additional 2 persons working also on other UVVM issues. They don't all work full-time on this, but there are also quite a few other people who has a knowledge and has been involved in this project earlier. I think if we receive something, an urgent bug, an urgent problem, we will do that and fix that definitely as soon as possible, and that would normally be within a week or two. If it's just things that are not that serious, we will normally have that in a next release, and that release would be speeded up if it's a sort of a semi-important issue, and that would normally take a few weeks, maybe a month. If it's only a suggestion for improvement, that is something that will be evaluated from case to case. Some suggestions will never be implemented, both because they might break the structure, there might not be sufficient need for it, as we think. But we try to be supportive of good suggestions from users. And very, very important, users can definitely provide pull requests. This is on GitHub. Provide a pull request on GitHub and explain what you've done. And then either we will include that pull request, or we will look at it and ask you maybe to do some minor modifications, because we have to make sure that everything is always working with the general structure. And then if you then submit a new pull request, we will put that into the system. So, and the same applies if you have a verification component that you want to share. Please let us know. We can put it out in the UVVM repository, or if you want to have it in your own repository, let us know and we will link to it. Any other questions?
No, I think that's all the questions. Thank you, Espen. Thank you ever so much for that.
Yep. So with that, thank you very much.
That's perfect. Thank you everyone for joining. And the presentation and recording will be up on the website at some stage later this week. Thank you very much. Okay, thank you, Espen.
Yep, thank you, Alison.
Okay, thank you. Bye.